All right, let's take a look at the fourth problem here. This problem asks us to use source transformation to find the Thevenin and Norton circuits. So we have a circuit where we have our typical uh, A and B, positive, negative. They call it VAB here, same thing as VOC. And now with source transformation, it's a little bit different of how we can do this. Where we were talking about before in the concepts, how you can take a battery that's in series and turn it into a current source that's in parallel, and likewise back and forth. So this is kind of a shortcut way of doing things. It doesn't always work, but when it does work, it's very, very useful. So if we want to determine the R-Thev, V-Thev, then I Norton, what we can do is we can come in here and initially say, like, okay, let's go and find R Thevenin first, just for the sake of getting it done real quick. We'll come in here and replace this with a wire, and we'll get this circuit. $100, $200, and then $150. A and then B, we're working that way. This will be parallel, and then after we combine those, these will be in series. So R parallel will be 100 times 200 over 100 plus 200. This will give us 66.67 ohms. Then R series will give us 150 plus 66.67 ohms. R series, which is equal to R Thevenin, will be 216.67 ohms. All right, so we got the easy part out of the way. This part doesn't require any source transformation. Okay, but the source transformation part is just going to be where we're going to try to determine V Thevenin and R Thevenin, or I'm sorry, I Norton, without actually doing the typical methods that we've been using. So if we want to use source transformation, what we'll do is we'll take the original circuit, and we see that we have a battery, and then we also have a series resistance. And what we'll do is come over here, we'll replace the battery with a current source, and we'll bring that current, or the resistance, down in parallel with it. And we will drop the rest of these in here. This will be B, this will be A, and now this will be I. And how do we determine I? Well, I is going to be V divided by R, which in our case here will be 24 divided by 100, which will give us 0.24 amps. Okay, so this will be 0.24 amps. And now what we can do is we can look at the new circuit, and we see that these are in parallel. So we can, oh, and I forgot one resistor here. This is 150. And now what we can do is we can say if we wanted to find the current that goes down through this branch or this branch, that will be broken up from here and there. No current will go down that way, no current will go down that way. Since these terminals are in parallel with this one and this one, all we need to do is determine the voltage across one of those branches, and we can figure out the voltage across the open terminals. So I will call this one I1, I'll call this one I2. And let's not forget, this is VAB over here. So to find I1, we would need R parallel over R branch times source current that's being broken up. And in our case, R parallel will be 100 times 200 over 100 plus 200, which we determined to be 66.67 over here. So this would be 66.67 ohms over our branch, which is 100 ohms. And then our current source, we said, was 0.24 amps. So therefore, it's 0.24 times 66.67, 100. That will give us 0.16 amps for I1. And we have the option of either doing the current summation, or we can do another current division. Excuse me. If we did I2, R parallel over R branch times I of S, we already determined 66.67 ohms over 200 ohms times 0.24 amps. About 200. And that should give us 0.08 amps for I2. Okay, or likewise, you could do I of S is equal to I of 1 plus I of 2. You'll get the same result. Okay, so now that we have these, all we need to do is for V of 1, which I'll call that one V of 1, and this one will be V of 2. So V of 1 will just be I1 R100, which will be equal to 0.16 amps times 100